Okay, dear students, in this clip, we're going to be going over the second example on how to connect the graph, connect f prime and f double prime with the graph of f. So for the given function, we have to answer questions A to D. Part A, we have to find all critical points and potential points of inflection. Part B, we have to generate a sine table for f prime and f double prime. Part C, we have to use the first derivative concavity test on the answers in part B to find where the function is increasing, decreasing, where it has its extrema, concavity, and points of inflection. And then finally, we have to sketch a possible graph of the function f. So for this example, the function we are going to be considering, this is number 2, is y equals 3x to the fourth minus 8x to the third plus 6x squared plus 1. Alright, so we're going to start off by answering part A, which is to find all the critical points and potential or possible points of inflection. Let's start out by finding the critical points. Critical points. Alright, so we know the critical points are the points where the derivative y prime is either equal to 0 or does not exist. And we know where the derivative does not exist is when you have a cusp, corner, vertical tangent, or a discontinuity. Okay, so those are the things we're going to be watching for in the derivative of this function. So to do that, let's rewrite the original function. The original function is y equals 3x to the fourth minus 8x to the third plus 6x squared plus 1. The derivative y prime is equal to 12x to the third minus 24x squared plus 12x. Okay, so in this function, this is a cubic polynomial that's continuous. It doesn't have any cusp or vertical tangent, so we know the derivative will always exist here. So let's focus our attention on solving for when y prime is equal to 0. All right, so let's go ahead and do that. So in order to solve this, we're going to solve the equation 12x to the third minus, let's try that again, 12x to the third minus 24x squared plus 12x when it is equal to 0. All right, so we're going to factor this and then solve it. All right, so here we can factor out 12x. So if we factor out 12x, we'll be left with x squared minus 12x plus 1 equals 0. All right, so let's factor this quadratic trinomial here using the x game. So if I set up my x, AC in this case is 1 and b is negative 12. So let's see, okay, I made a mistake here. If you factor out 12 from 24, I'm left with 2x, or else I can't factor that. So there's supposed to be 2x right here. Okay, so that's more like it. So AC is 1, and then B is negative 2. All right, so we can see that what works here is negative 1 and negative 1. So since the coefficient here is 1, I can go directly into the factored form. So this is going to be 12x times x minus 1 times x minus 1 equals 0. Okay, so to find our critical point, we will just set the factors to 0. 12x equals 0, or x minus 1 equals 0. We have a double root here, so I can just solve one of them. So in this one, we have x equals 0 and x equals positive 1. So our critical points are x equals 0 and positive 1. Okay. All right. And then we're to also find our potential points, or possible points of inflection. All right, so before we start looking for that, I just need to make a real quick remark here. When we're looking for critical points, we're looking for where the derivative is equal to 0, non-existent. And I stated earlier that y prime is equal to does not exist. And where does y prime not exist? never, because the derivative always exists in this function. This function does not have any cost, corners, vertical tangents, or discontinuity. So y prime being non-existent is not applicable in this situation. All right, so let's just keep that in mind. All right, shifting attention to the second part of question of part A, which is to find the potential points of inflection. Possible points of inflection, let's write that down. So possible points of inflection, possible points, could be one or more of inflection. So to find the possible points of inflection, we're going to look for the points where the second derivative is equal to 0. Okay, so where y double prime is equal to 0. Any value that satisfies that equation, that will be considered a possible point of inflection. All right, so what we're going to do, let's start by writing down the original function. Y is equal to 3x to the fourth minus 8x to the third plus 6x squared plus 1. All right, the first derivative that we found earlier, y prime was 12x to the third minus 24x squared plus 12x. Now we're going to find the second derivative, y double prime. Y double prime is 36x squared minus 48x plus 12. Okay? So all we just have to do here is set it equal to 0, set y double prime equal to 0 as we indicated here, and solve. All right, so let's go ahead and do that. So we're going to have 36x squared minus 48x plus 12 equals 0. If you notice, this has a GCF of 12, so we can factor that out, factor out of 12, and we're left with 3x squared minus 4x plus 1 equals 0. Okay, so let's factor this using the x game. So AC is going to go on top and B will go on the bottom. All right, so AC is 3, B is negative 4. What works here is a version of 1 and 3. So negative 1, negative 3. Okay, all right, so let's use that to factor this. So we're going to have 12 times 3x squared minus x minus 3x plus 1 equals 0. Bring that to 12, we can factor out 3x, x minus 1, factor out negative 1 here, and then we have x minus 1 equals 0. So the factored form is going to be 12 times 3x minus 1 times x minus 1 equals 0. All right, so this 12 right here, we can divide both sides by 12. That shouldn't be a problem. Let's multiply. We can divide by 12 or multiply both sides by 1 over 12. So multiply this by 1 over 12, this entire equation, and then multiply that by 1 over 12. So we'll be left with 3x minus 1 times x minus 1 equals 0. And then we use the zero product property. 3x minus 1 equals 0. And x minus 1 equals 0. If we solve both of them, we're going to have x equals 1/3 for the first possible critical point, and then x equals 1 for the second possible critical, point of inflection. All right, so possible points of inflection, are x equals 1/3 and 1. Okay. All right, so those are our answers for part A. Now for part B, what we're going to do is generate a sine table using these values that we got here. Okay, the first one or the first derivative will tell us the sine of f prime, and this one will tell us the sine of f double prime. Okay, so let's go ahead and set up our table. Part B is going to be for the sine table. Part B, sine table. right, let's scroll up and see the instructions. Just to refresh my memory real quick. Okay, it says generate a sine table for f prime and f double prime. All right, so I'm going to make an interval. We don't have any restrictions on our domain here. So we don't have a closed interval. It's like an open interval. So let's do this. My first, well, let me make sure I graph this. I do this correctly. Um, okay. So let's put the arrow. So that's my first line, first number line. We have, how do I calibrate? The denominator, I'll focus on the denominators of the fractional results here. So there's only one fractional result and it has a denominator of 3, so that tells me to go by 3's, okay? The smallest number I have is 0, so I put a 0 right here. So 0, and then 1, 2, 3, let's call that 1. Yeah, I think that's good enough. So yeah, we have 1/3 here. 1/3, 0, 1. That's all we need to care about. Okay, so we have arrows in this problem because it's not a closed interval. So on the this upper column, upper row, sorry, right here, is going to be the sine of f prime. Okay, we're going to divvy up the sine of f prime into the following intervals. So I have 0 and 1. I don't even need to put the 1/3 here. It doesn't really apply here. So 0 and 1. So this would be the first interval from negative infinity to 0. And then the next one will be from 0 to 1. And then the last interval will be from 1 to infinity. Okay? So let's label our intervals. Let's enumerate them. I'm going to call this interval 1, interval 2, and interval 3. All right? Okay, so let's pick test numbers here. So what number here was good? How about we test -1? So for here, I'm going to use x equals -1. Between 0 and 1, how about we use x equals 1/2? And then from 1 to infinity, how about we just pick x equals 2? All right, so these are the numbers I'll use to determine the sine of f prime on this interval, okay? So let's go ahead and compute them. I'm going to title this sine of f prime. And then we know what f prime is, right? F prime of x is 12x to the third minus 24x squared plus 12x. Now you have to, it's good to write down what you're dealing with here because we have 3 functions, 1, 2, 3, and you want to make sure you're substituting it into the right function. Okay, so since we're looking for the sine of f prime, we're just going to be inputting our test values into the first derivative, or f prime. Okay, all right, so let's start with the first candidate, which is interval 1. We picked the candidate of -1. So let's try x equals -1 and see what the sign is. Okay, so for that one, we're going to look for f of -1, which is equal to 12 times -1 to the third minus 24 times -1 squared plus 12 times -1. All I care about is just the sign. Okay, so let's work this out and see if we can figure out the sign as soon as possible. This will come out to -12. This will come out to -24. And this is -12. They're all negative, so we know that the answer is going to be a negative answer. So in this first interval, the sign of f prime is negative. Okay, negative. All right, let's look at the second interval, interval number 2. We're using x equals 1/2. All right, so let's look for f of 1/2. That's going to be 12 times 1/2 to the third minus 24 times 1/2 squared plus 12 times 1/2. All right, let's simplify this. We're going to have 1/2 to the third is 1/8, so we're going to have 12 over 8 minus 1/2 squared is 1/4. 1/4 over 20. Let's leave this as 24 over 4. I don't want to simplify it yet. And then this one is plus 12 over 2. I'm just going to leave them as a fraction, okay? All right, so why am I leaving it as a fraction? I want to find the LCD so I can easily compare them. Okay, so how does this compare with that? If I divide this by top and bottom by 2, I'm going to have 6 over 4 minus 24 over 4 times this top and bottom by 2 to get identical denominators with the rest, plus 24 over 4. We can clearly see that these two add up to 0, and you're left with positive 6 over 4. So this interval is positive. So we have a positive sign for f prime on interval number 2. All right, let's shift our attention to interval 3. We have the candidate x equals 2, so we have to find f of 2. Just substitute, I'm sorry, f prime. I failed to put the primes here. Sorry about that. F prime of 2, so let's go ahead and do that. 12 times 2 to the third power minus 24 times 2 square plus 12 times 2. Remember, all we care about here is the sign again, okay? So 2 to the third is 8 times 12 is 96. Minus 2 squared is 4 times 24 is 96. Plus 12 times 2 is 24. Alright, we see that these first two add up to 0, and then we're left with a positive number, 24. So this is also positive. Alright, so the sign of f prime is positive on interval 3 from 1 to infinity. Alright. Alright, now we need to find the sine of f double prime. Okay, so let's go ahead and find the sine of f double prime. I'm going to draw an identical number line underneath this one right here. So let's go ahead and draw that. So I have an identical number line. The same calibration, but then intervals are going to be different, okay? So this is 0, and this is 1. Okay, yeah, this is 1, 0, 1. So for our possible points of inflection, we're looking at 1 and 1/3. So 1/3 is right here. It's 1/3. Let's put it here, 1/3. And then this is 1, okay? So down here, I'm going to put, this is for the sine of f double prime, okay? So let's indicate our intervals. The first one will go from negative infinity to positive 1/3. The next one will go from 1/3 to 1. And then the last one will go from 1 all the way to infinity. All right? So let's alphabetize our intervals. I'm going to call this A, and then call this B, and then call this C. All right, we need test values for these three intervals. For A, how about we use x equals 0? It looks convenient. For B, how about we try x equals 1/2? And then for C, we can just use x equals 2. Okay, so what we're looking at now is the sine of f double prime. All right, sine of f double prime. So sine of f double prime, it's good for us to know what the function that we're dealing with is, so we don't get confused. So let's just write it. F double prime of x is equal to 36x squared minus 48x plus 12. So this is what we're going to be plugging our test values into to determine the sine of f double prime. All right? So let's start with interval A. We're going to be testing x equals 0. So what we're looking for here is f double prime of 0, which you can clearly see is just 12, okay? Because if we have 36 times 0 squared minus 48 times 0 plus 12, the zeros cancel out all of this, so we're going to end up with a positive result. Okay, so on the first interval, f double prime is positive. All right, and then let's look at interval B. We selected x equals 1/2. So we're going to look for evaluate the second derivative at x equals 1/2. F double prime of 1/2 is 36 times 1/2 squared minus 48 times 1/2 plus 1/2. Plus 12. Remember what we're looking for again here again is a sign. We're trying to see if it's positive or negative, okay? So this is 1/2 squared, which is 1/4. And then we are going to have 36 over 4, which is 9, minus 48 over 2 is positive 24 plus 12. All right? 9 plus 12 is 21. If you subtract if you subtract 24 from 21, you end up with negative 3. So this is a negative number. All right, so that tells us that on interval B, f double prime is negative. All right. All right. Now let's test the last interval. We're going to be using x equals 2 to test interval C. So let's go ahead and do that. So for C, x equals 2. So we're looking for f double prime of 2, which is 36 times 2 squared minus 48 times 2 plus 12. All right, if we work this out, 2 squared is 4. 4 times 36 is 144 minus 96 plus 12. We can see that this clearly is a positive result. All right, so over here, f double prime is positive. Okay, so we are done with part B, creating our sine chart. Now, we can now go ahead and advance to part C, which involves describing the behavior of f. Okay, so let's go back up to part C. It says use the first derivative in concavity test, and part B to say where it's increasing, decreasing, extrema, concavity, and points of inflection. All right, so let's start off with where it's increasing and decreasing. So let's see. If f double prime is negative, that means the function is going to be increasing. I'm sorry, keep getting opposite. If it's negative, that means the function is decreasing. If it's positive, it's increasing, and if positive here is increasing. Okay. All right. So let's go ahead and write that down. So for part C, we have it in. We can call this behavior of f. Behavior of f. Okay. So increasing. Where is it increasing? It's increasing on from 0 to 1, union 1 to infinity. All right? And it's decreasing. It's decreasing where the first derivative is negative. So that's from negative infinity all the way to 0. All right? Next thing we'll have to find is the extrema. That's, we can easily determine what the extrema are using the first derivative test. So this one changes from decreasing to increasing. So if you're going down and then you start going up, this extrema is going to be a minimum. All right, so this is a minimum. And then there are no other extremas. So guess what? Since this is the only minimum there is in the entire domain of this function, is also our absolute minimum, is our local and absolute minimum. We're confident about that. So what we have is we have a local and absolute minimum min at x equals 0. Okay? Right here, we have the local and absolute min. All right, after it hits this point, it just keeps going up after that. So those are all the extrema that we have. Just only one, so an extremum. Now we're going to look at the concavity. So to determine the concavity, we need to look at the second derivative. All right. So if we look at the second derivative, wherever it's positive, is concave up, and then if it's negative, f is concave down, and if it's positive, f is concave up again. All right. So that should tell us the intervals of curvature. So concavity. Concave up. The graph is concave up from negative infinity all the way to 1/3. Union 1 all the way to infinity. Okay, and then it's concave down from, let's see, where is it concave down? From 1/3 all the way to 1. That's where it's concave down. All right, so points of inflection. Points of inflection are the points where the concavity changes from up to down, or where the second derivative changes from positive to negative, okay? We have two of them in this problem. So here, point of inflection, and then also here, you also have another point of inflection. All right, so our points of inflection are at x equals 1/3 and 1. So points of inflection at x equals 1/3 and 1. That's where you have your points of inflection at. Okay? All right, so one key thing you want to note in this problem is that we have two critical points, but only one extrema. Okay, so that shows you that not every critical point is an extrema. In this case, we had a critical point at 1, but it turns out that it's not an extrema. Okay, so we have to be careful about that. But the sign chart does help us determine everything, okay? All right. Now, part D, we're going to sketch the graph. All right, so to sketch the graph, let me just unite these two tables, and that should tell me everything that I need to know in order to sketch the graph. All right, so let's go ahead and combine these two tables together. So I can just bring this down to here, bring this down to here, bring that down to there. All right, so this piece at the center is simply going to be the behavior of the function f. Okay, in this interval right here, from negative infinity to 0, it's going to be decreasing. That's what f prime. Let me use different colors so you can see. So it's going to be based on what f prime told me. It's going to be decreasing, and then the concavity from downstairs we know is going to be decreasing and concave up. And this interval, I know that it's going to be increasing because that's what f prime is in that interval, is positive, and then concavity is still concave up. Concave up. In the next interval from 1/3, remember this is 1/3 all the way to 1, f prime is positive, so it's going to be increasing, and then the concavity, f double prime is negative on that interval, so it's going to be increasing but concave down. And then the last but not the least, from 1 to infinity, f prime is positive, which means f is going to be increasing. F double prime is positive, that means it's going to be concave up. Okay? So that's what we're going to use to generate our graph, all right? So let's go ahead and do that. So what I'm going to do is calibrate my x-axis using the way I did my number line. So let's go ahead and do that. So something like this. Starting from 0, have 0 right here, 0, 1/3, 2/3, and then 1. Okay, so this would be my x-axis. Let's draw my y-axis. Now, just to get an orientation of my points, I can quickly discern that what my y-intercept is. If I set up my x-axis to 0, I can see my y-intercept is 1. So I know that the graph is going to intersect the y-axis at 1. So let's call this 1 right here. 1, 2, 3. The more points we graph, the more accurate our sketch will be. So let's say it goes through there. Okay, so from the graph, we know that 1 is a, what was 1? We had a local minimum at 1. So it was decreasing and concave down and concave up all the way to 0. So decreasing and concave down just means it's going to be descending, but it's going to be curving facing upward. So it's going to look something like that. And then we know this is a minimum, right? So it's increasing and concave up all the way to 1/3. So we can just make it look something like this. Increasing and concave up all the way to 1/3. And as soon as it hits 1/3, it is still increasing, right? But the concavity changes to concave downwards all the way to 1. So all the way to 1, you have something like this, concave down, and it's still increasing. Boom. And then when it hits 1, this is 1 right here, concavity changes again. Remember, we have a point of inflection at x equals 1. And now concave up, and it's still increasing. Okay? So concave up and increasing looks something like that. So this is basically what the sketch of the graph looks like. You can clearly see that this is our local and absolute mean. Let's go ahead and label that. So this is our local and absolute minimum. All right, and this point right here where the concavity changes at 1/3, that is a point of inflection. Okay, point of inflection. All right, so that's that. Okay, so let's go ahead and connect this with the result we just had. Let's see. Let's use dotted lines here so we don't get confused. So from this interval, all from here to here, we have something going on. From here to here, we have something going on. From here to here, we have something going on. And then from here to here, we have something going on. Let's see if we can connect the graph with, with our results, okay? So on this interval right here, it's decreasing and concave up. So that's what it looks like, going down and the curvature is upwards. From this interval from 0 to 1/3, it's, what is it doing? It's increasing and it's concave up still. All right? And then from 1/3 to 1, it's still increasing, but the concavity changes to concave down. And on the last interval, from 1 on upwards, it's increasing, but the concavity changes again to concave up. All right, so that's basically illustrating the connection between the graph and the results we got from the sine table. Okay, so hopefully that helps you get the main gist of the whole process. All right, so let's label this as D. This is the graph. This is D, the graph. So thanks so much for taking the time to watch this presentation. Feel free to subscribe to my channel by clicking here, and please post a comment to let me know what you think about this clip. And if you liked it, do give me a thumbs up. I appreciate it. And feel free to share with your friends, okay? More clips can be found on mathgosep.com/calculus. Thanks again for watching.